Welcome back again. Our last speaker of today is Professor David Huse from Princeton University. Professor Huse is a well-known expert in many fields, including statistical physics, phase transitions, quantum many-body physics of ultra-cooled atoms, many-body localization, magnetic ordering in materials and spin models, superconductivity, and out-of-equilibrium quantum dynamics. Today, he's going to speak about quantum thermalization and many-body localization, some fundamentals of quantum statistical mechanics.
Thank you. Yes, and thank you for the invitation to speak. I'm going to speak at the blackboard. I hope the change is refreshing, where you get to actually see the speaker in the blackboard. Okay, so my talk today is sort of two topics: quantum thermalization and many-body localization. They are opposites of each other, as I'll tell you. But first, the most common behavior of quantum many-body systems isolated from their environment is thermalization. And so I'll talk about that. And then given the time, we'll see how much time is left. I'll talk about one of the cases where it doesn't happen, which is many-body localization. And so, yeah, these are fundamental questions about equilibration, you might say ergodicity. And the reason this is now an active topic, research topic, is due to atomic physics. So atomic physics has moved to many-body physics very strongly with the advent of ultra-cold atoms and their descendants. And so one can make the kind of isolated, strongly interacting systems in the laboratory that we're talking about and study the kinds of questions we're talking about here. And then also the quest for developing quantum information processing systems has very similar issues. You try to build an interacting quantum system and isolate it from the rest of the universe. And ask what it does. You want to control, in this case, you really want to control what it does. In this case, you just want to understand what it does. Okay, so what we're going to talk about, so I've drawn a box here. And inside this box, we're going to put n degrees of freedom, and they're going to be interacting. The box is because it's completely isolated from the rest of the universe. So that's an idealization. But the atomic physicists are actually pretty good at approximating that rather well. And these degrees of freedom could be spins, they could be qubits, they could be the sites of an optical lattice that you may or may not occupy with an atom or a molecule. They are interacting. Let's say it has a generic Hamiltonian, which might actually depend on time, because you might have some external classical things you're doing to change the Hamiltonian. And we're going to take the thermodynamic limit and ask some fundamental questions, both the limit of an infinite system and the limit of infinite time. Okay, now by generic, what I mean is I'm not going to talk about some special cases, which, as far as we know, are fine-tuned. You have to have, a particular Hamiltonian, and it's not robust to arbitrary small changes. So there's the beta-Ansatz integrability, what I call traditional integrability, where there's a lot of special cases which can be exactly solved, and a lot is known, but they're special cases, and that's not what I'm going to talk about today. Not that it's not interesting, it is interesting, but I'm not talking about it today. And then more recently, the concept of many-body scars has been developed, and that's also very interesting. Those of you who know about that, I'm just putting this here to say I'm not talking about it. And those of you who don't know about it, I'm not going to talk about it, so you won't learn anything about it. Okay, so but the idea is we have a Hamiltonian, and I'm looking at the behavior that is robust to making small, local, short-range changes to this Hamiltonian. It's not fine-tuned in any way to any special behavior like these are, as far as we know. Okay. Now, we're going to start our system in an initial state. In general, it's a mixed state. So that's time zero, a density operator. And the initial state, let's assume, is observably. So I've underlined important points. So I'm going to talk about what I mean by observable. So the initial state is observably out of thermal equilibrium. But the initial state has conditions such that a proper thermal equilibrium does exist, and that equilibrium has extensive entropy. So that's the kind of initial state I want. When I say no cats here, so for example, you could start an initial state in a system with a Hamiltonian and conserved energy that was a superposition of low temperature and high temperature, right? And then if energy is conserved, it will always be a superposition of low temperature and high temperature, and it will never go to thermal equilibrium, right? But that's basically a Schrödinger-Cat state, right? It's a linear superposition of two macroscopically different states. And so let's just rule that out, that it has a thermal equilibrium. So if it has a temperature, it only has one temperature. It doesn't have multiple temperatures. Basically, what it means in that case is the energy density has a delta function distribution in the thermodynamic limit. So there's really only one temperature. There's a misspelling here, equilibrium. Okay, and then the question we ask is this fundamental question is, does this Hamiltonian dynamics generated by this Hamiltonian, does it bring our system to thermal equilibrium? And I do intentionally give the Hamiltonian a time dependence because there's different cases. There's cases with time independent Hamiltonians where you have a conserved energy and you go to that thermal equilibrium. But then you can also have driven systems where H has a time dependence and the equilibrium you go to is different. So I have that time dependence in there intentionally. Okay, so this is a yes/no question. And there's really two cases, which are the two phrases in my title. If the system actually goes to equilibrium under that dynamics, that's what we mean by quantum thermalization. And what it means is the system is acting as a bath for itself, right? We're asking the question, is this system a bath that can bring all its parts to thermal equilibrium with each other? And in your statistical mechanics class, you basically always assume yes, right? You have a system, you take a large system, you let it go to equilibrium, you wait a long time, you assume it goes to thermal equilibrium, right? And so this is the normal answer, and it is what normally happens for most systems. But there are systems for which that's not true, and that includes some of these special cases I said I'm not talking about, as well as many-body localization. And the many-body localization is a situation where, although the degrees of freedom are interacting, they don't form a bath. And instead, the system stays Anderson localized near its initial state. And for that reason, there's local memory. So the degrees of freedom have some memory at long times of how they were out of thermal equilibrium in the initial state. The system doesn't thermally equilibrate. So that's sort of the agenda for my talk. So I'm going to start with thermalization and try to define things a little more precisely. Okay, so thermalization, this topic has a history. Let me just mention a couple of some of the important papers. So there was an early paper by Jensen and Shankar, 87, and then Josh Deutsch, 91, Srednichi '94. But this was all before the advances in atomic physics and quantum information. So this stuff was mostly forgotten. And then it was brought back by a very nice paper by Regal. Okay. And this was published in Nature, so it got quite a bit of attention. And this is sort of when this topic got its modern start, although it had been going for a while, of course. Okay, so I have to define what I mean by thermal equilibrium. And so I'm going to define a thermal state. So the thermal state is a state of the system that is in thermal equilibrium. And this is well defined in the limit of an infinite system. It's not sharply defined necessarily in small systems. And so what it means is we have an n goes to infinity limit that gives a state, or we could say an ensemble. So in quantum mechanics, a single wave function is an ensemble, right? It's a probability distribution. So the distinction between a state and an ensemble, it really isn't a distinction in quantum mechanics. That is equivalent to the usual stat-mech ensembles. So in statistical mechanics, we know about the equivalence of ensembles in the thermodynamic limit, microcanonical ensemble, grain canonical ensemble, whatever. There's a sense of equivalence, which is if you take the thermodynamic limit and look at a small subsystem, they give exactly the same probability distributions, right? But I want to just generalize that to any state that has that property, and it's an enormously larger set of states than the ones you read about in your textbook. Okay. But we have to say, what do we mean by equivalent, right? So what does equivalent mean? And this is really, going over what you learned in your stat-mech course, but maybe I'll say it a little bit differently. And some points there would be emphasized differently. So what it means is the same probability distributions of observables. And I keep underlining the terms that need another definition, right? So when we say the different statistical mechanical ensembles are equivalent, this is really what we mean. We look at a small subsystem of the system, and whichever ensemble it's in, the probability distributions of the states of that subsystem are the same in those different ensembles, right? And that's why we can use whichever ensemble is convenient to do equilibrium statistical mechanics. Okay, but there's a point to be made here about observables that I want to emphasize. So in your quantum mechanics class, you learned that all observables are Hermitian operators. And you might have been told that all Hermitian operators are observables. But that second statement is only true for finite systems with a few degrees of freedom. And so what I want to emphasize here, and some of you may know this, but I think it's not generally understood, so I want to say it. In the limit, in the thermodynamic limit, n goes to infinity, almost all Hermitian operators are not observable. And this is essential to understanding how systems do go to thermal equilibrium. How do they forget their initial state? Okay, and now, I apologize to those of you who know this, and I'm telling you something you already know, but I think it's not generally appreciated. So let me just give an example. So let's say we have n spin 1/2. Okay. Okay, so as you know, this has 2 to the n basis states in its Hilbert space of the possible wave functions of the system, but it has 4 to the n operators. And for each spin, we have the identity operator, the x, y, and z Pauli operators, and then we can make operators that are products of any one of these 4 Pauli operators on each spin. So there's a total of 4 to the n Hermitian operators when you have n spin 1/2. But then if you ask how many of these are observable in the limit n goes to infinity, almost all of them are products of an infinite number of operators and therefore not observable, right? So when I say something is observable, what I really mean, it could be observed in principle in an experiment, right? And that really means it has to be a finite order operator in terms of the basic degrees of freedom, right? And so that's my definition of an observable. An observable is some operator that only involves a finite number of degrees of freedom. And in practice these days, that might be 10 degrees of freedom, right? Atomic physicists, do manage to measure multi-spin operators or multi-site operators up to some order, but it's always a finite number. And if we do take the thermodynamic limit, those are, almost all operators are infinite order in that limit. Okay. So I guess I got space down here. So I'm going to draw my system again here. So here's my system. It's in the box. And now I'm going to draw a subsystem, which I'm going to call little s. Right. So this is some subset of the degrees of freedom of the whole system. And then the rest of the degrees of freedom, which we could call S bar, the complement of S, all the other degrees of freedom, or let me just call it B. And when we ask about thermalization, the basic question is, does this subsystem see the rest of the full system as a bath? And then that bath brings this subsystem to thermal equilibrium. That's what the question about thermalization is, right? And so, okay. So if rho is the state of the full system, and in general, it's a mixed state, then the state of the subsystem S, which is some small set of degrees of freedom, let's say a finite set of degrees of freedom, they don't necessarily have to be near each other in space, but I've sort of drawn it that way here. This is equal to, what is the state of this system if I ignore the rest of the system? And so that just means take a partial trace over all the other degrees of freedom on the state of the full system. So this is the density operator of the full system. This is what's called the reduced density operator on this finite subsystem. We just take a partial trace over all the other degrees of freedom in the full density matrix. Okay. And then a thermal state is then defined that again, you have to take the limit. So really, this is a sequence of states, and this is a sequence of states. The limit of rho s is equal to what it is in some thermal equilibrium, and that thermal equilibrium is the same as what it would be in one of the standard Stetnik ensembles. So for example, we could say trace over B of the Gibbs distribution at a given temperature, chemical potential, or whatever thermodynamic degrees, thermodynamic parameters specify your equilibrium. Right? And so this is a Gibbs-Boltzmann distribution. Right? So if the state of our system in the limit n goes to infinity satisfies this for all subsystems for a particular equilibrium condition there, that's a thermal state. That's what I mean by a thermal state. All subsystems are at thermal equilibrium. Okay. Okay, so as Joel talked about earlier, or Neumann talked about, almost all states are thermal states. That's typicality. So how do we end up with non-thermal states? Of course, that's a basic question about the arrow of time and everything, but we are out of equilibrium. That's just an experience, that's just an observation, and that allows us to make non-thermal initial states. We can prepare states in the laboratory with entropies well below that of thermal equilibrium. But then after we do that, the time evolution is unitary. Let's say we have a time independent Hamiltonian, well, no, actually, yeah. So the time evolution is unitary. And that looks like this, that the state of the system at time t is equal to a unitary operator that gets you from time 0 to time t times the initial state. This is out of equilibrium, dagger, right? So this is out of equilibrium in some way which is observable. So there are many observables in this state that are not in thermal equilibrium. But then we time evolve it. And the question is, at long times, does it go to a state that is at equilibrium, and all that non-equilibrium behavior in the initial state is hidden. It's not gone, it's hidden. Right? Because this evolution is unitary, every feature of the initial state is in the final state. We could just run this backwards and I could write the initial state in terms of the final state. So the fact that the initial state is out of equilibrium, that information is present in this final state, even though this final state is in thermal equilibrium, right? So what's happened is all information, in quotes, about how rho of 0 was out of equilibrium. So this information was detectable with observables in the initial state because the initial state was out of equilibrium. What's happened is it has moved to non-observable operators for the final state. So in the final state, if the system has gone to thermal equilibrium, that's what's happened. Let me just say the slogan here. So thermalization is flow of information from observables to non-observables. This shows you why it really can't be sharply defined except in the thermodynamic limit, because it's really only in the thermodynamic limit that there is an infinite reservoir of non-observables which can take all your information about the initial state and hide it. Right? So thermalization, or going to thermal equilibrium in an isolated system, is not the system forgetting the initial state, it's the system hiding the initial state. Okay, I would just want to say one more thing here, and then I'm going to pause. I always like to pause for questions before I switch from thermalization to many-body localization. So if you have questions about what I'm saying, I'm going to give an opportunity for questions in just a couple minutes. I hope the chairman will let me do that. Right. Now, due to quantum systems have entanglement, so due to entanglement, quantum thermalizes in a stronger sense than classical. If you take a pure state of a quantum system that's out of equilibrium and the system thermalizes, it does go to thermal equilibrium in the way I defined it. If you take a pure state of a classical many-body system, what is a pure state of a classical many-body system? It is a particular configuration of that classical system. And then if it obeys Newton's equations dynamically, it will always be in a particular classical configuration of that system. And each of its subsystems is also in a particular classical configuration. So it never goes to thermal equilibrium in the sense I'm talking about, because what I mean by thermal equilibrium is at a given time, the probability distribution of the degrees of freedom in the observable is the same as equilibrium, right? Classical dynamics takes a single configuration to a single configuration. It never takes it to a probability distribution, right? But quantum systems can do that because of entanglement. You can take a pure state and it can become highly entangled, remaining pure, and that allows its subsystems to be in mixed states. And that way it takes a pure state and turns it into a mixed state under the reversible evolution, right? And so that's an important distinction that I like to emphasize. Okay, so that's what I wanted to say today about thermalization, which is the more important part of my talk. I'm gonna say some stuff about many-body localization, but I first wanna pause again, if the chairman will let me, and ask, are there any questions about what I've said so far?
Any questions of this part? Hari, please go ahead. Hari, you can speak now. Are you there?
Yes. Sorry for that. Yeah. So when you say a system is thermalizing, do you mean that it is thermal? There is a rate of thermalization. It's exponentially relaxing faster, or like it can also like thermalize on a slow time scale. That is one question.
I'm not addressing the time scale. That's a very rich and complicated subject of how long does it take to thermalize? What are the right ways of even quantifying that? That's a very interesting topic, which I'm just defining what would it mean to thermalize, and I'm just asking, does this happen in the limit of long time? Right.
Okay. Thank you. Yeah. If I'm permitted, can I ask one more question?
I'm not making any it's allowed to take, it's allowed to go to that thermal equilibrium extremely slow, and many systems do. I'll mention that later.
Okay. Am I permitted to ask another question?
Sure.
So if I compute some sort of local correlators on the asymptotic state, can I expect that they follow some sort of Kubo-Martin-Schwinger symmetry? I mean, do they satisfy some sort of fluctuation dissipation theorem?
Yeah, in thermal equilibrium, yes. Yes, it's standard thermal equilibrium, yes. And if it's just a 2-point correlator or something like that, that's an observable, right? It's just involving a small number of degrees of freedom. Yeah.
Okay. Thank you very much. Thank you.
I'm talking about standard thermal equilibrium.
Thank you.
Yeah, and the funny thing is the system could be in a pure state, just a single wave function. And then if you probe that state, you will see, the Kubo relations. Of course, once you probe it, you've moved it into some other state, but it doesn't have to be in an ensemble for those things to be true. It doesn't have to be in a mixed state for those things to be true. The pure state in quantum mechanics is an ensemble. Actually, let me mention another point here, which is this means that there are many perfectly fine statistical mechanical ensembles that are single wave functions. And one of them you are familiar with, which is the microcanonical ensemble, right? The microcanonical ensemble, you have a choice of, the microcanonical ensemble is all states in an energy interval, equally likely. And one choice you have is just to shrink that energy interval all the way down to where it contains only one eigenstate of the system. And if that system thermalizes, that's a perfectly fine microcanonical ensemble. That's the single eigenstate microcanonical ensemble, which is a perfectly fine equilibrium ensemble for a system that thermalizes.
Yeah, thank you very much.
That's the eigenstate thermalization hypothesis, which is true. It appears to be true for many systems, although it can't really be proven for any non-trivial systems. Numerically, it's very close to true.
We have one more question by Jose Gaite.
Yes, I don't understand the distinction you made between the quantum and the classical case, because in the classical case, you also have the ergodic hypothesis, and then the system evolves in such a way that occupies the most probable, the largest part of the phase space, and there are no particular features in it. So I think it is totally similar.
No, because I'm evolving it from a particular initial state to a particular finite time. I'm not doing any time averaging. So I'm just asking, I start in the initial state, it's out of equilibrium. I wait till some very long time and I look at exactly that time, only at that state, right? And in the quantum system, that is a thermal state. It is a thermal ensemble, even if the initial state was a pure state. Whereas in the classical system, that's one particular classical configuration. It is not thermal equilibrium ensemble. The probability distributions of the observables are delta functions on particular values. So that's the distinction I want to make. And I think there really is a strong distinction if you ask the question that way. You're absolutely right. If you do time averages, this is gone, right? But that's why I'm saying in a stronger sense. I'm not saying one thermalizes and one doesn't. I'm saying quantum thermalizes in a stronger sense than classical, right? I can define it such that quantum thermalizes and classical doesn't. But that's just within a particular way of defining it.
There is one more question by Peter Grasberger. Peter, you can talk now.
Following, take a drop of dye, find a drop of dye in a liquid, neglect diffusion but stir. And then in the long run, the drop will be more and more fuzzy, and not fuzzy, but spread out. And the observable fact about the fact of the ultimate view is residing in finer details which you cannot observe anymore.
Maybe you should type that in the chat and we can deal with it at the end. It was completely incomprehensible because there's just lots of static. So maybe I should go on. Is that okay with the chair?
Yes, it seems that there are no more questions, so you can go on with your talk.
Yeah. Okay, so I want to talk right now about many-body localization, which is a particular class of systems that do not thermalize. They do not, even though they are many interacting degrees of freedom, they do not form a bath. They can't equilibrate their own subsystems, and they can't actually equilibrate something else if you put it in contact weakly with something else. And this idea, of course, goes back to Anderson, but it was mostly neglected over close to half a century. And then there's, to me, a very important paper that brought this back to the modern era of discussion of this, which was Bosco, Alain, Altschuler, 06. And there are, of course, many other papers. That was true with the references I gave with the thermalization as well. There are many other important papers after that. Just early things. Okay, so what is many-body localization? This is Anderson localization with interactions. And in extensively excited states. So the usual discussions of Anderson localization are single particle localization, no interactions. So we're adding interactions and have many particles. And then there's a lot of discussions of transitions between Anderson insulators and metals or superconductors in the ground state, which are quantum phase transition. And I'm not talking about that either. I'm talking about at under conditions that would correspond to non-zero or very high temperatures. So that's what I mean. Extensively excited, meaning if it went to thermal equilibrium, it would have extensive entropy. So it's not anything near zero temperature. And so that's what's called many-body localization, which is abbreviated MBL. So it's sort of the hardest version of Anderson localization. It is there in Anderson's original paper. That's what Anderson started with. Anderson's original paper was about many-body localization in interacting spins, because it was about spins doped into semiconductors. But then he made certain approximations which reduced it to a single particle problem, and then people ignored the many-body part of the paper after that to a large extent. Okay, so just to introduce this, okay, so I'm going to take a trivial limit of many-body localization in a particular model. So this is a spin-and-a-half chain, and it has the Hamiltonian H equals H naught equals sum over the spins. So say we have n spins, and each spin is in a field. And this is the Pauli operator for that spin and a half. Okay, so it's just a bunch of spins, each in their field, and then all the H's are of different magnitude. So to keep the spectrum from having degeneracies, these fields are all different in magnitude from spin to spin. So this is true for all pairs. And so the spectrum doesn't have any degeneracies. So this Hamiltonian we know how to solve. All, the eigenstates are just spins either parallel to the field or anti-parallel to the field. And then the dynamics is the spins just do Larmor precession about their field. Each spin is doing Larmor precession about its field at a frequency that's given by the magnitude of the field. All those frequencies are different. So it's a chain of oscillators, all with different frequencies. And we can solve it exactly. It doesn't thermalize, right? I could start this with, half the spins pointed along the field, so they have high positive energy, and half the spins pointed opposite to the field, so they have low negative energy, and that energy will not be transported. The system won't equilibrate. So there's no transport, no thermalization. This is definitely localized. Now, this is trivially an integrable system in that it has integrals of motion, which are the, so each one of these spins, I can take its unit vector, each one of these fields, I can take the unit vector, dot it with the local spin operator. Let's call this tau n naught. These are all conserved operators which commute with each other and commute with the Hamiltonian. So we have a complete set of integrals of motion. So this is sort of trivially an integrable system. It has the structure that many-body localization has. And so let me just tell you what I mean by that. So let's now add weak nearest neighbor interactions, generic. Okay, so now the Hamiltonian is this H naught, which has these fields on each spin. And then I'm going to add some nearest neighbor interactions. So sum over n, goes 1 to n, some interaction, which might depend on and it couples sigma n to sigma n plus 1. I'm not going to specify what the interaction is. It just produces some interactions between the spins. It doesn't commute with these doesn't commute with these things, so it ruins these as good quantum numbers. But I'm going to make this weak. I'm going to put a parameter here, g, and then g is small. This is of order 1 typically, and this is small. Okay. And what's been argued first by them, and then actually let me just mention another paper, almost mathematically proven, but he had to make one assumption, by John Embry, 2014, for small enough G, this remains many-body localized. And what do I mean by that? I'm gonna just erase here. So what we do at, do this over here. So at small g, what we do is we dress the conserved operators. Okay, so this is the conserved operator at site n in H naught. So what happens is this conserved operator tau n is equal to what it is in H naught, and then we dress it perturbatively, so plus G times some stuff, multi-spin operators that are nearby to n, and then G squared times some stuff. So you perturbatively dress it. They perturbatively dress it. Embry showed that the non-perturbative effects are controlled mathematically, modulo one reasonable assumption. And then such that we keep these as good as conserved quantities, so that H commutes with tau n, and tau n commutes with tau m, and then the other key thing is that the dressing of the operator is localized. So the operator we're talking about in terms of the original spins, its support decays exponentially with distance for almost all n. So what many-body localization is, in our present understanding, is it's a type of integrability where the Hamiltonian has a complete set of localized conserved operators that commute with each other and with the Hamiltonian, with the same kind of structure as this trivial limit, except the operators are not so simple. They have some dressing, and some of them will have longer tails. It's a probabilistic thing. Now I was going to say one more thing before. Oh, yes. So, those of you know Fermi liquid theory. I use the word dress, and I'm thinking of that like in Fermi liquid theory. So in Fermi liquid theory, you have non-interacting fermions, not a Hamiltonian like this. You have non-interacting fermions, and then you turn on the interactions and you dress the quasi-particles to try to make them commute with each other as much as possible to give them as long a lifetime as possible. But there, you're not successful in getting the commutators to be zero, right? You dress the particle to become a quasi-particle, but it still has a finite lifetime, and it does decay. Whereas here, we're asking that we dress these conserved operators in the original non-interacting problem such that we maintain the commutators strictly zero. But that appears to be the case, modulo an assumption of perfectly plausible assumption that Embry made, appears to be the case for one-dimensional systems with short-range interactions. So you need to be in one dimension, and you need to have short-range interactions. If you have longer-range interactions, or if you have higher dimensions, it's believed that you cannot do this. And it's more like Fermi liquid theory, where it becomes very slow, but ultimately it does thermalize. So I think given the time, I have a lot more to say about many-body localization, but I don't really have time to say much more. So I think, I've just given you the essence of what we think many-body localization is. It's a new type of integrable systems. These conserved operators are specific to the particular Hamiltonian, particular fields, particular interactions. So it's a very different structure than the traditional beta ansatz integrable systems. And then the conserved operators are localized. And that's what the localization is. Many-body localized systems, the wave functions are not localized. In a many-body system, every degree of freedom has a wave function. So there is no localization of the wave function in a many-body system. What's localized are the conserved operators. And then there's an interesting phase transition as I turn up G, where this stops being true, you can't do this anymore, and the system thermalizes. So there's a phase transition as a function of G between a many-body localized phase, where you can do this, and the thermal phase, where it thermalizes. So it goes back to the behavior I was talking about in the first part of my talk. But I'll stop there and open it up for more questions. Thank you.
Okay, thank you, Professor Huse, for a very illuminating talk, or I should rather say lecture. Now we have some questions. The first one is by Martin Kaffer.
Hello, Professor. Thank you very much for your talk. I would like to ask you if this many-body localization phase transition, when you change G, it's reminiscent of the Kolmogorov-Arnold-Moser theorem, at least to me.
Yes.
Is there any no relationship, or other than, okay, yeah, they seem alike, or is there something more formal that has been done?
There's been a lot of discussion of that, and yeah, people are thinking along those lines, but I would say nothing particularly formal. So you could take a model like this and say, oh, this is not a spin, a half spin, this is a classical unit length spin. And then this is an interesting interacting classical problem. And we could ask, what about that? And then we're really asking KAM, although it's in the limit of large N, right? So KAM is understood when N is small, of order 1. But when you take the limit of an infinite system, even the classical KAM, I think there's no real solid results, although people please correct me if I'm wrong about that. But yes, you're absolutely right. There is a connection there. There must be a connection there, but it's still not clear what the connection is. And we're thinking about this. People are thinking about this. It's a hard problem.
Thank you very much. Again.
Now I am going to read the question by Peter Grasberger. He says, as regards classical absence of thermalization, take a finite drop of dye in a liquid, which is stirred, but there is no diffusion. As time goes on, the drop will become spread out, unfolded, until in the time to infinity limit, all information about it. And that's the end. I don't know if you understood what I said.
No, I'm not sure what the question is.
Because there's no
If it's a
question mark.
liquid, if it's a liquid, it has chaotic dynamics. And yeah, by the usual definitions, it will thermalize and diffuse, etc. But if it's, if there is a particular initial state and you follow Newton's equation, you end up with a particular final state, which is not the Gibbs distribution. And even 1 degree of freedom, if we ask about this atom, Is its velocity distribution the Maxwell distribution, which it should be if it went to thermal equilibrium? It isn't. It has a particular velocity, right? And so it's not at thermal equilibrium in the sense I was saying, right? Which is a very particular definition also, I admit that. All my point is that the quantum system is able to thermalize due to entanglement in a stronger sense than classical systems can, because they don't have entanglement as an option.
Well, it seems that there are no more questions. And before I close today's session, I'd like to thank all the speakers again and see you on Thursday.
Thank you.